push on with it. So hopefully we finish in about 3/4 of an hour or so. Okay, here's so topic 4, as we were discussing, is connection design. So what do we do? Well, put in context, we introduced connections. Now we introduced the design procedures for bolted connections. I've done, I think, at least one work example already in bolted connections. And then we're going to look at welded connections as well, and an example of welded connections in there. So as I said, we concentrated on the beam design previously, concentrated on individual members, a member in compression, member in tension. What we now need to do as well, we have to take the whole system together. What we've been looking at just there is what are the applied loads that we apply onto a structure. We take it down, we apply load factors in there and combinations together to make sure that our structure that we design is going to be safe. And the load goes down through a member, so in this case a beam. In another case it could be an axially loaded member, like a column, like a member of a truss in tension or compression. And that has to go down into a support and safely into the ground in there. So provision of the beam supports through connection design, either a pin joint, a roller joint, or fixed joint in there. So pins free to rotate, rollers free to both rotate and translate in one direction, and fixed means it cannot rotate or translate in any direction. Then we can make that connection either by a bolted connection or a welded connection, which is what we're going to concentrating on in this topic here. So as a design engineer, we're required to solve all the pieces of the puzzle for the design. We said that we put in connections if we have a change in direction, like for example a beam column connection or a beam connection, or the connection between different members in a truss in there. We also said that we might put in connections in there if we need to manage the size of a member for transport distances. For example, typically we don't transport steel over 12 meters, so we might have to put a connection in there if we need a member longer than that on site. Also for handling on site and moving the member around on site, and maybe because of the load, how heavy it is, and the crane or the lifting capabilities on site, or being able to move it into position might mean that we have to limit the size of a member. We also might want to change the size of the member. For example, a column going up through the building might have a larger member on the ground floor and first floor, and then we might reduce down the size of the member going up, because the demand on the member is less as we go up through the floors, because it's carrying less loading, because there's less floors being transferred, the weight of less floors, the loading from less floors are being transferred through the columns as you go up through the building. We classify the connections, either simple connections, fixed connections, or semi-rigid connections. Where simple connections are rigid connections, or semi-rigid connections. A simple connection is a pinned connection where it's free to rotate in there, so there's very little moment, or zero rotation stiffness at the end of the member. A rigid connection means it has a high rotational stiffness. Effectively, the rotational stiffness is equivalent to that of the beam, so the continuity is preserved with no rotation at the end of the beam relative to the column joint in there. Yes, in other words, the rotational stiffness is at least that of the beam. There's a semi-rigid connection somewhere in between a pin connection and a rigid connection, where it has some finite moment resistance in there. It's less than the moment resistance of the beam, so it allows some rotation but limited amount of rotation in there, and that's outside the scope of this course here. We said we have two kind of main types of connections. We have welded connections and bolted connections. We've talked about bolted connections in a bit of detail already. We'll hopefully get on to welded connections this morning. Effectively, there's two primary forms of welds that are in there, either fillet welds or butt welds that we use. So a butt weld here, where we prepare the end. So this is one piece of steel coming in, another piece of steel coming in, like here, one piece of steel coming in, another piece of steel. We put a chamfer or fillet at the end of it, and then we fill in weld material right the way in there. And we can assume that the capacity of the butt weld is at least that of the parent plate materials that we're trying to join together, or at least, sorry, the capacity of the weakest of the parent plate materials that we're trying to put together. Whereas a fillet connection is like on the left hand side here. There's a fillet connection. We have one member coming in here, a vertical member, a horizontal member, and then they're joined together by running a weld all the way along there where they join together. So that's like this T joint here, where the yellow shows the fillet connection, the grey is the plate material. We also have a lap joint. We have two plates flat on top of each other. One is moved over relative to the other, and we fill in there at that 90 degrees with a fillet. Or you can have a corner joint where we have two members and we weld in on the outside. That's a very unusual weld because it's relatively difficult to make. So fillet weld is normally preferred as it requires only simple preparation of the joint. The quality of the connection is particularly difficult because of defects below the surface or even minor flaws in the surface. They're difficult to see with your eyes, so therefore you have to do some non-destructive testing on them, such as radiography or ultrasonic testing that can be used. It's one of the main drawbacks of using on-site welding, and it's not typical to use welding on-site in Ireland. We typically do bolted connections on-site and welding within the factory in the fabrication centre. However, other countries, for example in New Zealand, they use a lot more welded connections on-site. I suppose they're more highly trained for it. It's more traditional to be done there than it would be in Ireland. The bolted connections will depend on the shape of the connections. So the bolted connection could be in tension, shear, or a combination of shear and tension in there. So we tend to use them on site, better quality control, faster assembly in there, and it can also have a significant influence on the building costs. So for example, normally when I'm pricing up a building, I'll work out what the mass is of all the primary elements, the beams, the columns, and so on. And then if I have simple connections, like in this case, I will then multiply the total weight by about 10% and then multiply that by the rate of for steel, like about €2 to €2.50 per kilogram of steel. Whereas if I have a bolted connection, instead of taking into account the weight of connections by increasing the overall weight of the building by 10% based on the primary members, I'll increase the weight by 20% in there. Okay, this is the book I had recommended. We went through designing the bolted connections in there. So we said it comes with lots of different grades of bolts in there. And when we looked at the table 3.1, we can tell very easily what the properties of the bolts are. So if we take the first number 6, the second number 8, multiply the two of them together, multiply by 10, that will give us a yield strength. So 6 by 8 is 48, multiply by 10, 480, that's the yield strength of the bolt. And then the first number multiplied by 100 gives you the ultimate strength of the bolt. Okay. There's within the design code, so Eurocode 3, part 1, part 8, it also tells us the maximum and the minimum values for the edge spacing. So this is the bolt hole. The bolt hole is normally 2 millimeters bigger than the bolt diameter. If it's a large bolt, it's 3 millimeters bigger than the bolt diameter. And then we have the distance from the edge of the plate to the first bolt hole in the direction of loading. It's known as E1. We have the pitch distance, is the distance between the two internal bolts in the direction of loading. Whereas the gauge distance is the distance perpendicular to the loading direction, and E2 is the edge distance perpendicular to loading. And then we have limits within the design code. So for example, if you go to figure 3.1 in Eurocode 3, part 1, part 8, it will tell us the edge distance has to be greater than or equal to 1.2 D naught, where D naught is the bolt hole diameter. D1 cannot be any bigger than 4 D plus 40, so T being the plate thickness that we're connecting that together. So that means that E1 has to fall within that range in there. Same thing for the pitch distance. We've got a minimum value for the pitch distance, a minimum value for the gauge distance, and so on, as we described in a previous lecture. So when we're checking for bolt connection, we check for shear failure of the bolt, where we can shear it across through it. There might be bearing failure of the bolt in the plate. There might be tension failure of the bolt if the bolt ends up in tension. There might be some buckling of a plate, which is outside the scope of this project, or this course, sorry. We might have to check the net cross-section capacity, like we did when we were looking at the member in tension. So where the holes are, we look at the cross-section there, maybe down through here or down through there. Look at the net cross-section area, multiply that by the ultimate strength, multiply by 0.59, and the material divided by the material factor of safety. And that will tell us the capacity of that plate in tension due to the holes in it. Okay, so we did the bolt shear check the other day, where we looked at the shear force in a member, which is this alpha V value, which is basically linked to the shear strength of the bolt. The shear strength of the bolt is the yield strength of the bolt, as if we were loading it axially, divided by square root of 3. And we use that for certain grades of bolt. Then those bolts that are less ductile, we would reduce that down to 0.5 in there. FUB is the ultimate strength of the bolt. A is the cross-section area of the bolt, which we typically use as 8T. And gamma M1 is the material factor of safety, or the partial factor of safety, which was 1.25. Okay. I put in some packing in there. We might have to reduce down the bolt capacity based on the packing, which we described in the other lecture. We also have to check if there's a long joint. So if we have lots of bolts together in there, then that could be a long joint in there. We need to, again, reduce down. If we have a long joint, we need to reduce down the shear capacity by this factor here, which we described in our previous lecture. And the reason is that is because we've assumed that the shear distribution is uniform throughout the joint in here. In reality, is if you have a long joint, you don't have a uniform shear distribution. Is higher, peaks down towards the ends, and less in the middle. So to take into account the actual shear distribution, we will use a reduction factor if you have a long joint. We did the bearing checks in there. The code has one formula for the bearing checks, which can be a little bit confusing. Sometimes it might be easier just to have 3 different formulas, but effectively it uses this alpha B value to take into account the 3 different checks. So if we look on the other part of the formula, FU dt, dt being the cross-section area, d the diameter of the bolt, t is the plate thickness, FU is the ultimate strength of the bolt. So that's a force multiplied by this factor, and then divided by the material factor of safety and K1. So that factor is to take into account the different bearings in there. So whether it's edge bearing, where the bolt is bearing against the edge out here and might fail as a result of that. We have bolt bearing is the middle one. So again, the bolt is bearing against the plate, so therefore we might fail. The bolt itself might fail in bearing. So the cross section D of the bolt times the thickness is what we have up here in terms of the area. And then the last one, where 1 is just plate bearing in there. So if the plate itself ends up failing as a result of bearing in there. Okay, so we went through that in detail the other day, where we have the different formulas. The only one that really we have to do a bit of calculation on is alpha D. We're given the formulas for the in bolts and for the in bolts here, and for the inner bolts here, where E1 is the edge distance, D0 is the bolt hole diameter, E1 is the pitch distance, and D0 is the bolt hole diameter in there. And then the K1 value, it depends if it's an edge bolt or an inner bolt. So an edge bolt, like in this case here, number 1 is an edge bolt, directional loading. Number 2 is an inner bolt and directional loading. And the K1 value is equal to E2, which is the distance to the edge perpendicular to the loading. And D0 is the bolt hole diameter, 1.7 in there. P2 is the gauge distance in there. Okay, so we worked out what the K1 values were. So all of that information is all summarized in this one table, in table 3.4 in Eurocode 3 part 1 part 8, where we check for shear, check for bearing, and also we may need to check for tension resistance if we have a bolt in tension. Okay, and because in our connection we might have a group of fasteners in there, and when we check for shear, we check for bearing. Sometimes it might be, say, the edge ones, it might be bearing conditions, might be driving it, whereas the inner bolt, it might be shear that's driving it. And this other one here might be, say, bearing that's driving it. So each bolt in a group of bolts, it might be a different thing that's driving the capacity, because the shear might be lower than the bearing, or one of the bearings might be lower than the shear. So if we're designing the whole joint, then we look at it. So if the shear resistance is greater than all the bearing resistances, then it's obviously the bearing resistance for each of these is going to dictate the capacity. So the overall resistance is equal to the sum of the bearing resistance. Otherwise, the design resistance is the number of bolts by the minimum of the shear resistance for each bolt and the minimum of all the bearing resistances in there. Okay. So we did an example on that, where we had 2 plates that were joined together. We're pulling up on this 10mm plate, pulling down on the 12mm plate. The first thing that we notice is that both plates have the same material properties, S355. They're less than 10mm, less than 40mm thickness. Therefore, table 3.1 in Eurocode 3 part 1 part 1 tells us that Fy is 355, Fu is 470 newtons per millimeter squared. Because one plate is thicker than the other, we only really need to concern ourselves with the thinner plate, because everything else is similar within the plates in there. We also know that it's grade 8.8 bolts. So 8 eighths is 64, multiplied by 10 is 640. That means the yield strength of the bolt is 640 newtons per millimeter squared. And the 8 at the beginning multiplied by 100 gives us the ultimate strength of the bolt of 800 newtons per millimeter squared. If we can't remember that, we go to the table in Eurocode 3 part 1 part 8, and we get it straight out of that. They're M20 bolts, so the diameter of the bolt is 20 millimeters. So that means the hole diameter that we have to drill in the plate to accommodate the bolt is 2 millimeters bigger, so 20 plus 2 is 22 millimeters. If E1 is 35, we P1 is 90, P2 is 200, E2 is 55 millimeters. So they're all the dimensions that we needed. We went to the blue book. In there, went to page D303. We found a 20 mil bolt that gave us the area of it and gave us a shear resistance of 94.1 of the shear resistance. We also put that into the formula to check it as well, to make sure that was right. That was the shear resistance done. So we put that into the formula here, 0.6 times 800, the ultimate strength, multiplied by the cross-section area of the bolt, divided by 1.25, that gives us 94 kilonewtons, 94.1 kilonewtons. Then we check for the bearing resistance, where we had to check for the different rows. So we had row 1, row 2, row 3, row 4. This is a 10 mil plate. We pull up this way. That means this row 1 is at the edge, it's at the end, because as we pull it up, it's only got this distance here away from the end, which is 35 millimeters. So we use the formula in the table 3.4, which is this formula at the top here. And we check K1 alpha B FU D times D. So K1 we checked as the minimum value of this formula here. We got out that K1 is 2.5, alpha D as the edge bolt. In there we got that as 0.53. And then the alpha B value that we put in here is the minimum of alpha D, FUB over FU, or 1, which we put in there. Minimum of those three that we just worked out, and then came out to be 0.53, which tells us that alpha D, which is the edge bearing, is the one that's driving the design here in this case. Okay, and we did the same. And then once we knew alpha D, we could put in the formula. We had worked out K1, 2.5. We know what the ultimate strength of the plate material is. Bolt diameter, plate thickness, material factor, safety, we get 99.6. And we did the same then for the other 3 rows, row 2, row 3, and row 4, where we worked out what the K1 was value, minimum of all of that. These are internal bolts, alpha D then, because an internal bolt, we're using this formula here, P1 over 3 times D naught minus a quarter. That works out to be 1.11, because P1 is 90, as per the diagram down here at the bottom. Alpha B then is the minimum of alpha D, FUB, which is the bolt ultimate strength, FU, which is plate ultimate strength, and 1. So we put those in, and we get 1.11, we get something bigger than 1, and we get 1. So therefore, alpha B now is equal to 1. So at the edge for row 1 here, we said it was edge bearing that was driving, because it's alpha B is being dictated by the edge bearing, which is alpha D. Whereas in this case, the bearing, that bearing isn't driving at this time. Neither is the bolt bearing, but what is driving is the plate bearing. So that's the one that's going to cause these plates, this failure within the internal bolts, will be that the bolt would bear first before any of the other bearings happen. I'll get that as 188. But bearing in mind that we checked also for shear failure, and each bolt has got a shear capacity of 94.1 kilonewtons. That's smaller than the edge bearing of 99.6 for row 1. It's also smaller than the bearing capacity of all the other 6 bolts internally. So therefore, what's driving the design of this connection is the shear capacity, which is 94 kilonewtons. So therefore, the overall capacity of the section, of the bolts, the bolted connection is the 8 bolts that we have multiplied by the shear capacity of each bolt, and that gives us 752 kilonewtons. We checked if it was a long joint in there, as the length of the joint that we have here. And we found out that it was greater than 15D, just about. So we would have a reduction factor of 0.99. So we multiply the total resistance of the connection and reduce it down by 0.99. So it's around 150, or maybe a little bit less, is the total capacity of that bolted joint. Okay, so that was that example. Quickly run back through and the theory behind it. So I'll just do one more of these examples in the bolted connection, and then hopefully get on to the welded connection as well. So here's a bolted connection. So last time we only had 2 plates. This time we have 3 plates. So we have a plate in the middle, a 12 mil plate in the middle here that we're pulling down on, with 2 10 mil plates either side that we're pulling up on. So this time in this example here, we've got basically double shear in there. Okay, so if I had the bolt going across, There's the bolt head. There's the nut on the other end. Bolt coming down. Okay, so I've got a 10mm plate here. Okay, so I have a 10mm plate there with a load coming up here. This is an elevation I'm drawing, another 10mm plate here. And then going down the other direction. I've got okay. So I have P down there, I was saying P over 2 and P over 2 at the top here. Okay, so that's the 12mm plate going down the way. So I'm pulling down with the 12mm plate and down the way. And then the other two 10mm plates are pulling up the way. So what does that mean for the bolt? Well, we can see now the bolt that I've got shear in two planes now. I have a shear plane here and a shear plane there. So I've got double shear in this case. Okay, so I have a double shear in here. Whereas last time I had only single shear because I have two shear planes here, one there and one there. Okay, so double shear in my in my solution in there. Last time was a 10mm plate that was the driving one. In this case here, so we know here that it's the 12mm thick plate governs. Okay. Why? Because we have two plates that are 10mm thick each. The 2mm plates about 10mm thick each, so that's 20 in total. Whereas we have only 12 going the other way. So we've got equivalent to 20mm thick plates going up the way and 12 going down the way. So therefore, it's the 12mm thick plate that governs this time in our check. Okay. If we remember for the shear capacity of bolt, we made single shear equals 94.1 kilonewtons. Here we have double shear. Okay, so here we have double shear implies F V or D equal to 2 times 94.1 kilonewton per bolt, which is 188 kilonewton per bolt. Okay, so that's the shear. That's the shear check in there. Okay, so then we have to look at the different bearing checks. So that's shear. Okay, so shear capacity is checked there. That's shear. Now we have to look at the different rows. So last time, if you remember, I had row 1 down the bottom because it was the 10mm plate that was determinant. So that was row 1 is the first one nearest to the edge. In this case, we know it's the 12mm plate that's going to be the one that's driving the values in terms of the bearing capacity in there. So now I put row 1 at the top, row 2 next, row 3 next, and row 4 after that. So the next check that I need to do is the check for bearing. Okay. So I'm going to check bearing as the next thing I'm going to do. So I checked for bearing last time for the edge distance. So if you look at what the bearing check in here, we have K1 times alpha B FU D times D. So K1 is a minimum distance along here. So K1 is the same in this case because we haven't changed all the layout of the bolts is the same. All we've done is we put an extra 10mm plate on the outside. So in this next example, K1 is still going to be equal to 2.5 in there. And also alpha D hasn't changed. E1 times 3 times D0, that's the same. We have E1 is 35, D0 is still 22 in there, so that hasn't changed either. So none of these values have changed at all. So therefore, the bolt resistance for row 1 in this case is going to be, in this example, it's going to be the same as what it was last time. Okay. Okay, so for row 1, so as for example 1, it's the Q slide for 1 second. Q slide. There, someone's asking us to go back to the Q slide. I'm not sure which is the Q slide. This one. Okay. Okay, so as per example 1, what we said that we have K1 is equal to 2.5, and we had alpha B is equal to 0.53. So that implies that FBRD, so the bearing resistance of that one is K1, which is 2.5, times alpha B, which is 0.53, times the ultimate strength of the plate, 470, times the bolt diameter is 20, times the plate, in this case is 12, not 10, because last time it was 10 millimeters thick. This is 12 because it's a 12 one that dictates it, divided by the material factor of safety, and the partial factor of safety is 1.25. That's 120,000 newtons, which is 120 kilonewtons. Okay. So the big, the main change here from the example, for the first example, is it's the plate is 12 mil that's driving the solution rather than the 10 mil. So we can see that by increasing the plate thickness, we get to 120, whereas last time we were at, where are we at? We're at 99.6 kilonewtons. Okay, so obviously around 100 for 10 mil, increase that for 12 mil is 120 kilonewtons. Okay, so we've gone up from 100 kilonewtons to 120 kilonewtons in there. Then we go to the other rows, row 2 to 4, which are the internal bolts. So row 2 to 4. So again, we haven't changed the overall geometry of the plate. So as per example 1, we'll end up with K1 is equal to 2.5, and alpha B is going to be dictated alpha D, sorry, is 1.11. So therefore, alpha B is going to be 1. Okay. So alpha D is the edge distance edge bearing. So it's going to be plate bearing that drives the example here. So then again, FBRD. Again, it's the same formula as last time. I'll just write it out here actually, just to have it on this page. Okay. So K1 is 2.5. Alpha B is equal to 1. The ultimate strength of the plate is 470. The bolt is 20. The thickness of the plate is 12. All divided by 1.25. And that's 226 by 10 to the power 3 newtons, which is 226 kilonewtons. Okay, so again, the difference here between last example, this example is just this 12 millimeter plate that's dictating the design. So from the above then, we have F, B, or the minimum. So the minimum bearing resistance that we have there is equal to 120 kilonewtons, which is for the inner bolt. That's less than the shear resistance of the bolts, because it's double shear, which is 188 kilonewtons. But that 188 then is less than the bearing resistance of the internal bolts. So that's 226 kilonewtons. Okay, so last time was simple. We're working out the overall capacity of the connection because the shear drove everything, because the shear was the smallest one. In this case, we have the inner bolts, or the edge bolts, the bearing is only 120. Because it's double shear, the shear is 188. And for the inner bolts, the bearing is 226. So therefore, it's going to be the bearing is going to determine the capacity for the edge bolts, and it's going to be shear that's going to determine the capacity for the other ones. Sorry, the shear would happen. So what the code has told us is, it says, look, we can, if we go to close 3.7 Eurocode 3 part 1 part 8, that tells us that the overall joint resistance is going to equal to the number bolts times the minimum bearing resistance, which in this case is just 8 by 120, which is 960 kilonewtons. Okay, so that's what the code will tell us to do. I will say, well, let's take the lowest of all of those bearing resistance. Let's go back to where the code tells us that. I think I pulled it out here. Okay, so the design. There it is. So design resistance of a group of fasteners will be taken as the sum of the design bearing resistances of the individual fasteners, provided that the design shear resistance of each individual fastener is greater than or equal to the design bearing resistance. Okay, so it's the sum of the design bearing resistance if the shear resistance of each individual fastener is greater than or equal to design bearing resistance FBD. So it's not in this case, because some of the bearing resistance are higher than the shear, some of them are less than the shear. It says otherwise the design resistance of a group of fasteners should be taken as the smallest of the fasteners. Should be taken as the number of fasteners multiplied by the smallest design resistance of any of the individual fasteners. Okay, so in our case, some of the bearing resistance, some of the fasteners, so the internal 6, the bearing resistance is higher than the shear. The external 2, the edge 2, bearing resistance is lower than the shear. Okay, so therefore we don't meet the first part of the clause. So it says otherwise the design resistance of a group of fasteners should be taken as the number of fasteners. In our case, we have 8, multiplied by the smallest design resistance of any of the individual fasteners. So that's what we've done in the example here. Okay, so 8 fasteners multiplied by the smallest of all of the resistances, and the smallest value of all of these 3 is the 2 edge fasteners, which have a bearing resistance of 120 kilonewtons. Okay, any questions on that? No? Okay. Okay, so then on to welded connections. Welding is the process of joining metal parts by fusing them with heat using electrical current. So we have 2 pieces of steel here together, and to fuse them together with a metal, 2 pieces of metal, 2 pieces of steel, we fuse them together, basically put an electric current going through in there, and we're going to fill them with metal from the electrode. So the electrode is connected here onto the welder, and then we're going to fuse these together by passing electric current to the electrode, and that's going to deposit fitting material, weld material in there, and it's going to fuse the 2 elements together. The fillet weld is the most widely used, as I mentioned previously. Fillet welds often fail in shear in there, so there's a failure plane across there. Shear failure occurs along the plane through the throat of the weld. So this is the throat of the weld here. We're looking through a cross section of the weld. One plate coming down here, another plate coming down through there. We fill in here with the fillet, and then this is the throat thickness coming up here, which is 0.7 times the area here, or times the leg length here. A is the leg length. Okay, and that's a 3D image of the failure plane there. So that's the failure, and then Eurocode 3 part 1 part 8 4.5.3.3 presents a simplified method for design of fillet welds. Foot welded connections in there. So as I said, you treat the end of it and prepare the end of the steel in there by chamfering off the end, fully filling it up with weld material. That's a full penetration butt weld in there, and you can prepare the end of it various different ways. Usually a V is the most common one. You have a single bevel where you only prepare one side as a chamfer, keep the other one straight. You can have square, which isn't very common because it's difficult to finish. Double bevel you could have where you put a chamfer on both sides and fill in between. Okay, so complete joint penetration butt weld, so transmits the full load of the member that you join together. So effectively, we can assume that this joint here is as strong as the base material that it's connected to. And partial penetration butt welds, the welds don't extend completely through the thickness of the piece that's being joined. So if we look at design of the fillet welds, we've got some general rules in there. So if we have overmatched the electrodes, then we can say that the ultimate strength of the weld is equal to the ultimate strength of the material. So therefore, the simplified method tells us that the resistance of the weld is equal to the shear resistance of the shear strength of the weld material times the A. So A here being the throat thickness, and then the shear resistance of the weld being the strength of the material if we load it axially divided by square root of 3. That's the shear strength, which is what we've used before. We've got this beta W value that we can get from table 4.1, and then we have the partial material factor of safety, which is 1.25 in there. Okay. And in our drawings, we can put various different symbols in there. So if we have one plate coming onto another, we have a fillet weld on one side, then we put an arrow down through, and then when we put the triangle or the flag underneath the line, that says that the weld is on the near side. So pointing here, it's near us on the near side. 6 is the size of the fillet weld in terms of 6 millimeters. If we put the triangle on the top of the line, that says it's on the far side. So even though I'm pointing here, the weld is actually on the other side as per the section over here. If I have the triangle on both sides with a 6 beside it, that means it's 6 millimeter fillet weld on both sides, near side and far side, as per the sketch up here. If I put a circle around it at where the arrow comes out and changes direction, that means all around. So here I have the arrow or the flag below it, or the triangle below it, that says the near side. So it says the fillet weld all around on the near side. So we can see up here it's basically all around the perimeter of this steel piece. We have a weld on the near side. Okay, and that's the same on the other one here. So there's an eye section, and on the near side, so outside of all the edge here, we put a fillet weld all the way around, fully around it. So the circle around is fully around. And if you want a sight weld, you put another little fill-in flag here if it's a sight weld in it. Again, this is a 10 millimeter sight weld on the near side because the open flag is on the underside of the arrow. Okay, so very quick example here. So we have connect a pump. So we want to connect a member together. So we've designed a fillet weld, 6 millimeter continuous fillet weld. So we use CFW for continuous fillet weld. We're going to connect two plates together. We want to design that weld in there. Okay, so we might have one plate here and another plate here, and that could be the fillet weld that we want to design in between the two of them. Okay, so we'll assume they're S275 plates. So we'll assume that the plate thickness plate thickness less than or equal to 40 millimeters. That implies Fy is 275 newtons per millimeter squared, and the ultimate strength is 410 newtons per millimeter squared. Okay. We know that the strength of the weld, shear strength of the fillet weld design is equal to Fu divided by square root of 3. So that's basically the shear strength of the weld material divided by beta W times gamma M2. Okay, and then so beta W, we normally take that as being 0.85. You get that in table 4.1 in the code. So if you look up the code, you get that in table 4.1. Okay, so we have 410 divided by square root of 3 all over 0.85 times the material factor safety 1.25, and that gives us 223 newtons per meter squared. Okay, and then the strength of the weld. So it's a force F W or D going to be equal to the shear strength, the design shear strength, weld times A, and then in this example here we have a 6 millimeter continuous fillet weld, so A is equal to 6 millimeters. Sorry, A is equal to 6 millimeters divided by √2. Okay, because we have, let me draw the weld over here. Okay, so we said it's 6 millimeters. So I want to work out what A is, which is this value here. Okay, so the leg length is 6 millimeters. So 6 millimeters divided by square root of 2. So that's 223. Multiplied by 6 divided by square root of 2. And that's equal to 945 newtons per millimeter run. So every millimeter we have of that weld, it has a capacity of 945 newtons per millimeter run. Okay, so that's a very quick introduction to weld design. Very, very simple weld design. We can come into a bit more detail when we come on to design in our project.